The question that I asked at the end of last lecture was, is a triangle more like a grid or a line? So what do I mean by that? I mean, when we make a triangle large and then we double it, does the number of dots in the triangle change more like the way the number of dots in a grid changes, or does it change more like the number of dots in a line changes? Well, to understand this, we really need to work out CT of n. Right? So what's CT of n? CT is the number of dots in a triangle of dimension n. Right? So essentially, in a right triangle, what is this called? A 45, 45, 90 triangle, where one side has length n. Well, we could do a couple of just checks here to see what it looks like. So if I have one dot, obviously, or if it's dimension 1, obviously I have one dot. If it's dimension 2, I have how many dots? I have 3. If it's dimension 3, I have 6. If it's dimension 4, the value of this is getting lower and lower. If it's dimension 4, I have 10, and so on. Right? So what is this actual expression for CT of n? So we'll do it the cheating way, where I tell you the answer and then I tell you how to go verify it yourself. So it turns out the answer is it's 1/2 times n plus 1. So now I'm going to show you a quick trick that you can use to actually verify this. And hopefully it's a trick you can use to convince yourself of this in the future. If you're having trouble remembering whether it's n plus 1 or n minus 1, and whether there's a half or a 2 or what. All right, so let's just look at this particular grid and use this grid to help us think about it. So I'm going to draw several other dots. So I'm going to draw some red dots to complete the grid. And so let me draw them like this. Right? Now notice that there are exactly twice as many red dots as there are white dots. Okay? Or if you're reading along in the notes, black dots. Okay, so what does it mean that there's exactly twice? Well, it means I could draw a line through this thing. I could slice it like this. And the number of dots I care about is on one side of this line, and then there's the same number of dots on the other side of this line. So if I can work out how many dots there are in this whole rectangle, right, if I add up all the white dots and all the red dots, and then divide that by 2, then I've got my answer. Well, how many dots are there in this rectangle? Well, so all together, there are n, right, this is n, times n plus 1 dots, n plus 1. So there's n times n plus 1. So how many of those dots are white? Half of them, right? So half that is n plus 1 over 2, which is just this expression. Okay, so that's how you can work this out, work out this expression on your own. Nobody ever showed this to me. I had to work this out myself a ton of times before I realized that this is easy. This is the easy way to do it. So there's your free advice for the day. Everything else is included in your tuition. So we've got this expression now. This expression that says CT of n equals 1/2 n times n plus 1. And so now let's compute the limit that we're interested in. The limit that goes like this, that says what happens when n gets large and then we double the input. So what we have is the limit as n goes to infinity of CT of 2n divided by CT of n. And so this equals the limit as n goes to infinity of 1/2 2n times 2n plus 1 divided by 1/2 times n plus 1. So we can do a couple things immediately here. First, we can cancel the halves. Right? Those go away. We can also cancel the ends. Whoops, not erase the ends. Not helpful. We can cancel the ends. Okay, those go away. And so now we have a simpler expression. It's not everywhere simplified yet, but we're making some progress. So here we have 2 times, oh, we can do one more thing. We can take that 2 and we can push it outside the limit. So let's go ahead and include that in what we do next. So we have 2 times n plus 1, 2n plus 1 over n plus 1. And I think I've got everything accounted for then. Eventually, one day I will have everything accounted for. Okay, here we are. Okay, so the n's are gone, the halves are gone, the 2 is outside, and all we've left is the 2n plus 1 over n plus 1. Okay, good. So what do we do next? We can split these apart if we want to, or I can just divide the top and the bottom by n and deal with it that way. So let me call this 2 times the limit as n approaches infinity of 2 plus 1 over n over 1 plus 1 over n. So just like we have before, focus on these two, and note that when n gets very large, those two are both going to go to 0, right? So this goes to 0, this goes to 0, and we're just left with 2 divided by 1, which is just 2. So in the end, what do we have? We have this thing equals 2 times 2, or 4, right? So which of the shapes that we've talked about before has this characteristic, right, where the number of dots quadruples when the dimension doubles? The grid, right? So what's our answer? The triangle is like a grid, right? In other words, if the triangle is very large, there is a very well-defined mathematical sense where it behaves exactly like a square, right? And in fact, it behaves exactly like any rectangle that has sides that are related to each other in some constant way. And you can think about this in the following way, right? Here's one of the ways that you can wrap your head around the idea that a triangle behaves like a square when it gets large, right? So let's think about a triangle, right? There's our triangle, and it turns out that here is one way where you can think of it as being like a square, right? Both growing no faster than a square and growing no slower than a square. I can take this triangle and I can say, and so that suppose this triangle is actually perfect and it actually has a 90-degree angle and two 45-degree angles. What I can do is I can draw a square on the inside of the triangle. And I can say that this square has a constant relationship. The area of this square has a constant relationship to the triangle. This square always has exactly half the area of the triangle, right? So the triangle, no matter how big it gets, is never more than twice as big as a square that's inside it, right? And that square kind of scales at the same speed as the triangle. It's also true that the triangle is never much smaller than a square, right? And what's that square that it's never much smaller than? Well, it's this one, right? The triangle is never much smaller than this square that it fits exactly inside, right? So one of the ways you can think of this statement, that triangle is like a square, is that it is both never much larger than some square and it's never much smaller than some square. Never much larger or smaller than some square. Okay. And so that wraps up our discussion of triangles, squares, and lines. I would encourage you to think about some other kinds of shapes. So, for example, you could do exactly this exercise with a different triangle, right? So you could do this triangle. Suppose I've got a triangle that has 4 dots in this dimension, and then only 2 dots in this dimension, right? So here's another sort of triangle-looking thing, and the bigger it gets, the more triangle-y it's going to look. But here you could ask the same question about this triangle, and you could say, is this triangle more like a square or a line? And you could make this extreme. So you could say the number of dots in the first row is 3 times the number of dots in the second row, and then come up with a way of generalizing that rule as this thing gets bigger, and ask, is that thing more like a square or a line as it gets very large? And I think some of the answers might surprise you. What you may find is that you can have a very, very line-ish triangle, right? This triangle looks pretty line-ish. But depending on how it's defined, depending on how that angle is defined, you'll discover that this triangle actually behaves more like a square than it does a line, even though it almost looks like a line because it's so thin. And we'll explore this mathematically in great detail in the homework, and then with respect to algorithms throughout the rest of the course. But here's the basic idea in terms of some really simple geometric concepts.